AG, I'll mark you later. Anyway, let's return to our vortex stretching. And so you might go back to your handouts right here. This is where we left off last time on 1.12. And of course, all these turbulent flows have strong vorticity in them in 3 dimensions. And you would imagine that the vorticity or your vortex fluctuations also fluctuate in the flows. And one major problem of, say, 2-dimensional turbulence, if there is such a thing, is that it would be totally non-physical. And I state why that would be in my second bullet point in 1.12, that in 2 dimensions, vortices can't stretch. And it's a natural tendency for these turbulent vortices to become sort of like a nice bagel or donut. And then you can imagine pulling them on the top and bottom out to become sort of like a long, hollow pasta noodle. And that's a natural progression of vortices. So if you're in 2 dimensions, you might imagine you have like your nice flat bagels and flatland, but they can never stretch, which is a natural dynamics of all turbulent flows. So that means that obviously there's no stretching whatsoever, and so there can't be no satisfactory turbulence closure without vortex stretching. And that's something that maybe catches a lot of people, because even if you solve the Navier-Stokes equations using direct numerical simulation in 2 dimensions, you will not be able to capture the true cascade of turbulence, which we'll see. I shall also note that for high Reynolds turbulence or low, you'll see these types of tubes, and I'll show them in the figure. So 1.8, let's go down and look at that. This is one figure I took off the internet, and it's basically Taylor-Green vortex, which is initial solution, and it's unstable, and it's going to break down into turbulence. And so here's 3 DNS simulations. Direct numerical simulation, meaning you're just using the computer to solve the Navier-Stokes equations. And these are discretized on 3 sets of cells, 50 cubed, 80 cubed, and 128 cubed. And so nothing has changed. And after 12 physical seconds, not computer time, right, because these are very expensive simulations, you can see that just by having increased resolution, you're increasing the grid spacing. But if you zoom into any of these, if it was higher resolution, you can find your own searches on the internet. You'll see that you have, of course, more resolution and more scales of turbulence. And you also say that these vortices, if you zoom in, are more elongated. And so you can't really produce simulations like this in 2 dimensions at all. Why? Because, of course, there's no vortex stretching. Okay. So this is really where I wanted to be on the 3rd class, or excuse me, this class today. And it's basically has 2 major objectives. One is to talk about the so-called turbulence cascade. And so we're going to look at a few more physical observations and then look at Andrei Kolmogorov's finding, his law about the spectrum of turbulence. And then we'll look at the law of the wall for boundary layers, which we'll need both these ideas in this class. So, of course, it's true that turbulence is a continuous spectrum of scales, meaning that if it's like in wave number, then there's some continuous spectrum, and they go from the tiniest scales to the largest scales, just like you might see up in these DNS simulations. And we're going to try and discuss these in terms of eddies. Of course, this is just a sweet term, sorry. And it's often asked, like, well, what is a turbulent eddy? Well, here's one particular definition. A turbulent eddy might be some sort of local swirling motion whose characteristic dimension, like length or time, is on the order of the local turbulent time scale. And so you might have a laminar vortice. That's not really considered turbulent. What's the difference between a turbulent vortex and a laminar one? I suppose if it has the condition of chaos. We might also speak of these in terms of wavelengths, and that might go back to kappa again, wavelength. And how would we find wavelengths in these types of flows? Well, it'd be through, of course, Fourier analysis. And if you take a Fourier transform and say a spatial direction, you get wave number. Just like if we took a Fourier transform in a temporal direction, we would get frequency. So remember, Fourier transforms in space would give us wave number, and they would have units of 1/meter. And if you look at these turbulent flows, if it's from a DNS or a natural visualization, you're going to see all these turbulent eddies, like in this figure here, figure 1.10, which is an experimental flow visualization of dye in water. And some of you have been lucky in your undergraduate studies to have done that, where you inject a dye in a water tunnel and watch the boundular eddies form. But you might look at, like, say, this is one particular eddy, and it has some particular length scale. Just call that L, and that has the dimensions of meter, so its wave number would go as, say, 2 pi over L, and you might have a factor of 2 pi or not, just depending on how you define your forward and backward transforms. Anyway, looking at these flows, you can see there's very large eddies, very small ones, and down near the wall they become smaller. And just so happens, if you take measurements and Fourier transforms, you'll find that L goes as Y, that the maximum length scale possible, the simplest turbulence model, if you will, would be that the length scale increases linearly from the wall. Anyway, the smallest scales, they don't exist forever, and they have the smallest time scales, and they go somewhere, and that is usually due to the viscous effects. So viscosity will convert small scales to, say, heat or entropy and acoustic waves. So all scales of turbulence produce some sort of noticeable acoustics, but the vast majority of energy is going into heat in the background of the flow. Okay? So let's look at some of these large eddies and other properties of turbulence. Generally, these large-scale structures, if it's a fully turbulent flow, contain smaller structures, and those structures contain structures, etc., all the way down to the smallest scales. So when you're talking about large-scale turbulence, you're talking about these large-scale eddies, which are convecting in the flow and carrying these smaller eddies. And I suppose that's where, like, that little poem came from, you know, that I showed in the syllabus in the beginning of the class. There's like whorls within whorls. In something like a boundular, you might imagine that there's some mean free path or flow, like this, if we take, say, u bar as a function of y, and this would be the edge of the boundular. And these large-scale structures can easily extend out of it. And that's a little bit of a problem, which we'll deal with in the later part of this class. It's also true that the large-scale structures have long lifetimes. And of course, the small-scale structures have the shortest ones, and those would be the Kolmogorov time scale. And in a typical boundular, like at low speed, high Reynolds number, sometimes the length scales would be on the order of, say, 30 times delta, which is the boundular thickness, just as a rule of thumb. And this was measured by Bradshaw, who you'll see in the literature a lot, in 1972, according to my notes, is just one of the many examples. In supersonic flows, like on a Concorde, you might have 50 to 100 times coherent length scales of turbulent structures in the supersonic boundular. So it's quite astounding to kind of look at the range of flow properties. Okay. Do you have any questions about that? No? We'll do some analysis on this in a second. Probably the biggest difference between laminar flow and turbulent flow is just this enhanced diffusivity. This enhances momentum, energy, mass transfer. And it's also true in the stresses. much larger than laminar flow. And you might also say that there's an enhanced viscosity. And sometimes that's why people call it that eddy viscosity. So, whoops, maybe I should write, I don't know why I always do epsilon, I'm sorry. But I should maybe write something mu t for like an enhanced viscosity. And so when you're making models, sometimes you might want to increase viscosity in the flow through some mechanisms or some equations. And that's a huge idea behind a lot of the models that are useful today and we look at. Okay, and some more notes on the smallest scales. These, as I mentioned earlier in these classes, are called the Kolmogorov scales, and they're usually the smallest scales of turbulence, named after Andrei Kolmogorov. And I noted before that we note that turbulence is a continuum phenomena, and one might ask, how can we estimate those scales without any experiments or computation? And it's very useful to try and estimate the small scales, especially when you're in a computational world, because you want to decide how many grid points you need to resolve certain scales of turbulence. Certainly I would want to meet the Nyquist criteria and have like 7 to 10 grid points per wavelength of the Kolmogorov scale. So we need to consider how to do this scaling analysis, right? So we might say, and just note that the dissipation of kinetic energy to heat will be done through the action of molecular viscosity. And I mentioned before that's happening at the smallest scales of turbulence. So it's likely, and this is like a major postulate that turns out to be correct, that the smallest scales are relatively unaffected by the largest. So philosophically, we might think that these large energy-containing scales of turbulence have within them contained many smaller eddies all the way down to the smallest little turbulent eddies that are just being carried through. And their dynamics are controlled more so through the viscous action, through viscosity and dissipation. So that would be dissipation and viscosity, mu. Epsilon and mu. Epsilon is dissipation and mu is viscosity. And this is really what came out of Andrei Kolmogorov's probably most famous paper in turbulence in 1941. And there are eddies, or these little Kolmogorov scales of turbulence. There's little things there. Should depend on some function, mainly of epsilon and mu. And we'll look at his arguments in a second. So that's what I wrote here, actually. Epsilon should go as negative dk dt at small scale, and viscosity, mu. Okay, so up here, this means that the rate of decay of the turbulent kinetic energy at small scales and through a huge part of the turbulent spectrum, which we'll look at in a second, goes as the dissipation. So let's look at some units of these, and I've wrote it down to kind of save some of your writing. We've already talked about dissipation. We derived the dissipation equation in previous class. And if you look at it, it has units of length squared per time cubed. And there's viscosity, and those units are length squared times time. So just looking at dimensional arguments without doing anything else, it's actually possible to form a huge number of different combinations of these two terms to find a length scale, a time scale, and a velocity scale. And in fact, these terms here are the Kolmogorov, ooh, I didn't want to vector, the Kolmogorov length, time, and velocity scales. So those would be like the scales of these smallest turbulent structures in any type of flow as an estimate. And it actually turns out to be extremely accurate, if not perfect for certain mathematical assumptions. Okay. So, make sure I'm on the right page here. Yep. So their length. So let's just give like some examples. So say you're in a car and your speed is 65 miles per hour. And say you're at the driver's side window. Your Kolmogorov scale eta, which is this term here, will be on the order of, let's see what I have here, 1.8 times 10 to the negative 4th inches. And your length scale, whoops, excuse me, I didn't want the length scale. Oh, I'm sorry, that's the length scale of a mean free path of a gas. That will be about 2.5 times 10 to the negative 6. And that's a collision mean, which is actually pretty big. Anyway, it just gives you an idea, and this is actually a pretty low Reynolds number flow. So let's get in and talk about how this is all going to be connected with Kolmogorov's theory. So turbulence is, of course, going to contain a spectrum of scales, and we're going to do our analysis in terms of a spectral distribution of energy. And I mentioned before that we have a wave number, and that wave number is going to go here as lambda equals 2 pi over kappa. Why? Because this has units of 1 over a meter, so the total units are meter. So that's our wavelength. And if we can estimate the length scale, we could put it in this equation and get a corresponding wave number. Higher wave numbers have smaller wavelengths. Low wave numbers have long wavelengths. And we want to try and do this analysis in terms of spectral distribution of energy. And before, we've already defined this equation, but I'll present it again. We have K as the turbulent kinetic energy. And we derive that as what? The trace of the Reynolds stress. But now I'm introducing a new definition to relate it. This is an integration of E of kappa. And E of kappa is what we call the energy spectral density or spectrum function. And I'll show a picture of what that might look for a high Reynolds number turbulent flow in a second. But look what the arguments are. It has kappa as the argument. So that's what? The wave number. So if I have an energy as a function of wave number, and I integrate it all, I get the total energy. So E of kappa is nothing but the energy on a per wave number basis. How do I get that from an experimental flow? Well, I might take hot wires, and I would try and measure the velocity fluctuations in a particular direction. Or I might take a CFD simulation, I take the velocity fluctuations along the line, and I could integrate all that, integrate along the line, and then all of a sudden I have a frequency distribution, but instead of frequency, of course, it's wave number, by taking a Fourier transform along the line. So of course that's nothing but a Fourier transform of, say, U of x. Something like that would get me U of kappa. Okay. So we know this is related to the Fourier transform. Now it turns out that for low wave numbers, you'll have the largest scales of turbulence. And that probably indicates to me what? That these low wave numbers, I'm going to have the most energy at the largest scales, but the energy containing scales. And we'll see that in a second. It also means that at high wave numbers, I'll have the smallest scales. And they have really a small amount of energy. And it's of course true that there's way more small scales, small eddies, than there are large ones. And if there's an energy balance that goes as dk dt goes as negative epsilon, then I would think that if I add up all the energy on all the smallest scales, that it would be balanced with the fewer larger scales. And So using the same type of arguments for high Reynolds number turbulence, Taylor, in his 1935 paper, wrote these equations. And they're very much related to the Kolmogorov scales. You can see here, epsilon will go as k to the 3/2 over L. K is turbulent kinetic energy, epsilon is dissipation. Those would be constant in these flows. And L is a length scale if it's stationary turbulence. And K, the turbulent kinetic energy, would go as epsilon times the largest length scale to the 2/3 power. Part of this theory, and you can see it by looking at simulations or just natural flows or clouds, is there's always tiny, tiny little eddies which have the length scale eta, right? And you have large scales. So we make this observation that L is much larger than eta, much larger. How much larger? Well, with increasing Reynolds number, you would expect that the range between the largest scales and the smallest scales of turbulence would keep increasing. And one might wonder, well, how does that work? Well, using equation 1.7 here, I might combine these and try and form a Reynolds number. So let's try and do that. So I will say L goes as L all over nu cubed over epsilon to the 4th. 4. And that might go as LK 3/2 over L to the 1/4, all over nu to the 3/4 if I just simplify it. And what is this term here that I've really written? LK to 3/2 over L to the 1/4, all over kinematic viscosity to the 3/4. Well, I have a length scale, I have a velocity scale, and I have a viscous scale to powers. And you can write that and note that's non-dimensional, and it goes as RT, which is this equation here. So you actually have defined, based on this dimensional analysis, a turbulent Reynolds number. So we can have Reynolds number that was defined like in your previous aerodynamics classes, where it has velocities, length, and viscous scale. Well, here we have one where we have a velocity scale, and that has, of course, K. It's an energy, so that's meters squared per second squared to the half. Then it has units of meters per second. Anyway, you can balance this out. You have a length scale and viscosity, and of course it has no dimensions. So that's what we call by the turbulent Reynolds number. So it's based on the characteristic velocity of turbulence, the viscosity of the fluid, and the integral length scale. And it has to hold for this condition. So this will not hold technically for lower speed flows. Okay. So I made these notes here already. I said them verbally. So you'll see in a second that Andrei Kolmogorov had to make these assumptions that the scales are higher, there's some universal spectrum of turbulence, and he sought to find it. And there's a whole range of eddies between the smallest scales and the largest scales, and those are called the cascade. It's the range of scales between largest and smallest. Okay, and why is it called a cascade? Because it's like the idea that energy cascades, kind of like down a waterfall, if you will, from the largest scales to smallest. And this will make a lot of sense once we see the spectral representation. So in Kolmogorov's paper in 1941, he wrote down this equation on dimensional grounds. Here, kappa, that's the wave number. And of course, it has units of per meter. And you can see here is 1 over eta, the Kolmogorov scale, and L is the integral scale. So this holds through the whole range of scales from basically the smallest scale to the largest. And he wrote that in this range, between the largest and smallest scales, the energy should be distributed like this. where C sub k is a coefficient. That's called the Kolmogorov constant. And epsilon is the dissipation rate of turbulent kinetic energy, which should be constant through that whole range. And kappa is the wave number. So this is called the Kolmogorov -5/3 rule. And a lot of times when people are doing CFD or taking experimental measurements, they'll actually plot a graph of kappa versus E, and they'll make it a log plot, and they'll put this -5/3 line. So of course, in the log world, it's a straight line, and they'll plot their data, the experimental data. Will go like this. And more often than not, you'll see that this -5/3 trend exactly matches experiments or CFD if you've done it correctly. And you'll see that a lot through the literature. Now, this is a certain range. It's not over the whole range, and this is called the inertial range. And this is where I plot it right here in this particular plot for you, which I stole from a book. But there's about 1 billion of these little plots in every turbulence book in existence. Okay, so let's look at this plot relative to Kolmogorov's famous equation. So here's this wave number on the x-axis. Here's E of k, the energy spectrum on the y, and here's this range. So out here, right, at high wave numbers, you have the smallest scales, and those are 1/eta. And down here, we have the largest scales of turbulence, right? So those are 1/L. And there's everything in between. Now, this black line here, you might view as an idealization. But if you take measurements and you do process the data, you'll get something that looks like that for a lot of different types of turbulent flows. And this is especially true and exact for homogeneous isotropic turbulence. So out here at this peak is the maximum energy of the largest scales of turbulence. So these are larger, but they don't contain as much energy as this point. And through this whole range here, we can plot this equation, epsilon 2/3 kappa -5/3, and draw that as the dashed line. And so this is not terribly impressive visualization of the graph, because this inertial subrange turns out to be often the biggest part of the graph and contain multiple decades. So this is a kind of like a low Reynolds number turbulence. And as you increase the Reynolds number, this inertial subrange, which is governed by this law, will increase. They call this the viscous subrange because that's where the energy is going into heat and a little bit of acoustics, entropy. It's the smallest scales. They're dominated by the viscous terms on the right-hand side of Navier-Stokes equations. Over on the left, these are dominated more by, say, just Euler equations, the evolution of large-scale structures. And viscosity plays little role in their general dynamics. Okay. So it's kind of dangerous to go down this approach. And I should mention that you can also form other dimensional quantities just by doing dimensional analysis. And you could do that and compare it with measurement data without doing anything else. And one example of a bad choice for a form of the energy spectrum might be epsilon the 1/4 viscosity to the 5/4 times some type of function that involves kappa and eta. And eta is the same. So this is really like a bad choice. And you can see up here, it's very much different. You got epsilon 2/3 kappa -5/3, same dimensions, but involving a little bit different variable choice. And it turns out if you plot this function, it's not going to match experiments or DNS simulations. So that can be a problem. And there's some authors who've kind of like explored these different choices, and they try to put Kolmogorov's work on a firmer theoretical basis. So there's obviously different ways to deduce these physical laws. But of course, the one that agrees with experiment and measurement is probably the one that we would trust. And in the work of Kolmogorov, he does it rigorously through making assumptions about what we call structure functions and homogeneous isotropic turbulence. A structure function is nothing but, like, we'll just call it I don't know, US equals something like U2 minus U1. So a structure function is the difference between any two particular velocities in space. And if you're in a turbulent field where space and rotational translation doesn't mean anything to statistics, then that helped him reduce that whole theory. So these were structure functions. Now, this is the old way of doing things, and it turned out that there's some authors, and they are Afzal and Narasimha. I'm going to kill their names, 1976, and they did a perturbation method. And they were able to rederive his laws. Now, I know I got some pages in this sheet on how to do that, but I don't want to spend too much time on like going through their analysis. I actually, in the interest of time too, and making sure I have enough time to talk about the computer project later and law of the wall, I want to point out some important points. One is I put here, and they noted that, and I'll read it, the viscous and energetic scales in a turbulent flow exists in an overlap domain over which the solutions characterizing the flow in the two corresponding limits must match as Reynolds number goes to infinity. And that's a really interesting statement in their paper, because also Kolmogorov, he assumes that the Reynolds number goes to infinity for his theory to be like exactly correct. But of course that's not practical in any situation, because of course you can have an infinite Reynolds number, but for very, very, very high Reynolds number turbulent flows, it turns out that these are correct solutions. It also has to assume that rate L is much, much bigger than eta in all of these situations. And that means in their work, they actually found through perturbation theory an overlap region between taking a lower asymptotic limit and higher asymptotic limit and matching these solutions in the middle in the inertial range. I think it's a more of a contemporary approach of like how they did these things. At the end of the day, I wrote down the major points of this, and they also rederive Kolmogorov's famous result. And so we're going to use this particular equation 1.82 in this class when we get to some modeling. Why? Because in certain situations, like grid turbulence, if you create a turbulence model and you run it against grid turbulence or fully developed turbulence, high Reynolds turbulence, the spectrum and energy decay, or if it's stationary, should all hold against this particular equation. Okay, so that's one major thing I wanted to point out today, which is Kolmogorov's result. The second one, and maybe more so important, is law of the wall, because a lot of turbulence models were developed to close boundary layer flows, right, where there's turbulence connected to a wall. And so let's look at that. I wanted to point out in this sentence that there's a streamwise velocity in the flow near the wall, and experimentalists noted that it would vary logarithmically from the distance of the surface. And that note from experimentalists and an early conference paper like Ludwig-Prandtl and I think that was a 1908 conference paper, which you can pull today, is where he outlined his experimental measurements and his analysis. Okay, and so what does that mean? That means that U in some region near the wall should go as the log of Y. So that's what was seen experimentally, and it's an amazing thing, and it holds in almost all high Reynolds number turbulent flows. They all have this like log law region, and it's really nice to know that, because if you do a CFD simulation or doing experimental measurements and you can't plot the log law of the wall, it's probably an error on your part. If it doesn't exist, it's could be something like a low Reynolds number flow, or maybe an internal flow because internal flows and external flows have slightly different relationships. Okay. A few things that we also notice is that the pressure gradient very near the wall is very small. And we actually make corrections to these profiles based on this assumption. So pressure gradient certainly affects things. Okay. I note that near the wall, the turbulent boundary layer is going to be established by two mechanisms, just like in a homogeneous isotropic turbulence, you have viscosity and dissipation. Here we might have a rate at which momentum is transferred to the surface. And we'll call it the shear stress tau. And the second is the molecular diffusion of momentum. And these are the two main forces, or physical phenomena, that we really need to think about. And this is also what Prandtl postulated in 1908 to form his theory. So how do you say this is valid? Well, one thing we have to do is define delta, and that's the boundary layer thickness. And that can just be think of philosophically as the distance from the wall to the edge of the boundary layer. And there's great ways to define that, and we'll look at that in some of our computer programming projects. So we might say that eddies close to the wall are small and grow with distance from the wall. And this is absolutely true because we've measured it. And also the shear stress is going to vary only a tiny bit with y. And we might look at, say, the surface shear stress in place of tau. We'll also denote molecular viscosity by mu. And we might also say, well, since the turbulence behaves the same in gases and liquids, and I guess plasmas too, it's reasonable to say that we might scale our results as tau w over rho and kinematic viscosity. So Prandtl says, okay, we got tau, molecular diffusion, and in place of these two experimentally observed parameters that matter in different turbulent boundary layers, we're going to try and scale and look at our flows as a shear stress at the wall, right? So that's the force tangential to the wall divided by the density at the wall, if it's compressible, of the fluid, and the kinetic viscosity. So in 1966, Landau and Lifshitz have tried to normalize these boundary layers by defining what we call the velocity scale or friction velocity, and that is u tau is the square root of tau w over rho. And of course, the units are meters per second. And this is a really important equation, and you'll see that when we look at turbulent boundary layers in the last computer project, you'll have to use this because you'll try and plot your results and log over the wall, and we call that the friction velocity. And it's really a velocity scale at the wall that has to do with friction, of course, but it's a scale of velocity. So we're trying to, the goal here now is to define that log law formula based on these dimensional arguments. So we're going to say that, and it's a postulate, that the mean velocity partial u partial y is correlated with u tau, viscosity over u tau, and the distance from the wall. And you can go through a Buckingham pi theory or do what Landau did and write down this formula. So we'll say that the partial derivative of u with respect to y, so this is the y direction, and this is u, and the boundary layer is going in this direction, it's turbulent, and there's some velocity profile there. It goes as the friction velocity divided by distance wall times some function of u tau, that's the friction velocity times the distance from the wall divided by viscosity. And they wrote that this is some universal function. But the question is, what is it? Well, they laid this out because they already knew the answer. And it's nice in life when you already know the answer, and they knew it was going to be some sort of like log function. So they took the asymptotic limit of this function in equation 1.84 and said that as it goes to infinity, it's going to go to a constant. And that would make sense because you would want partial u, partial y to become a constant. So when you take the derivatives on each side, u is going to be going to just a constant, which would be u infinity at the edge of the boundary layer, which is up here. And it turns out that's called today von Karman's constant after Theodore von Karman of Caltech. And it turns out to be usually 0.41 if you compare with experiments. So anyway, you can take this equation and integrate both sides, and you'll find the so-called law of the wall, which is here, and I'm going to write in with you. Oops, yeah, my page is mixed up. 38. Did I skip a page? Oh, I'm sorry, I went too far down. There it is. It's 1 over kappa. And this is von Karman's constant times the natural log of u tau y all over nu plus c. Here c is usually about 5, but we'll see this might change depending on roughness for smooth surfaces. And k is that von Karman constant, which is 0.41. And these were really shown in Klein's paper in 1969. So let's look up here at what an actual flow might look like. And this figure I think is super important. And I hope that you've seen this in your, if anybody's taken the turbulence class last semester or some point in your career. Okay, so we have the y-axis, that's y plus, and that's a non-dimensional distance to the wall. And the y-axis is u plus, that's this friction velocity, which we just defined, which is right here. And now this black line is something which looks like something we might measure. So if I take a hot wire and put it in a turbulent boundary layer and then took the average of the fluctuations and plotted it against the distance of the wall and put it in what we call inner coordinates, I would arrive at this profile, okay? So here we have what we call the viscous sublayer, and that's shown by this dotted line. And that's u plus equals y plus. If you've done these calculations correctly, u plus equals y plus equals 1 at this location. In the defect layer, or outer layer, you'll see this type of behavior, and this will be u infinity at this location. And then from the scales of like 10 to 10 cubed, which is 2 orders of magnitude difference, this is that log layer. And this is where equation 186 holds. Okay? So if you're really plotting this equation, you're really plotting this dashed line here. Now you might ask yourself, well, okay, there's only 2 orders of magnitude between 10 and 10 cubed. What happens if I increase the Reynolds number of the flow? What happens to the log layer range? Anybody want to take a guess? It gets smaller. So if I increase Reynolds number, so you say it gets smaller, but why would it get smaller? What's the intuition there?
Oh, I misread one of the things.
Okay. Yeah, it's actually the opposite. Yeah. It actually gets bigger. And so this viscous sublayer, that's called the viscous sublayer simply because viscosity is dominating the flow. We have the smallest scales of turbulence, the scales of turbulence on the order of the distance to the wall. Out here in the defect layer, you have huge scales of turbulence. In fact, these large scales of turbulence can exist through most of the boundary layer, but their center location is sort of located at a distance y from the wall. If I increase Reynolds number, I would expect the number of decades from 10 up to whatever the highest decade is to increase. So just like in the theory of Kolmogorov, where you have a negative wave number to the 5/3 power inertial range, that would increase with Reynolds number. We would also see that the log layer of a boundary layer increases. So the theories are actually in parallel, that they have a small scale and a large scale, and they're connected by some universal statistical function, which was calculated entirely by theory. And it does turn out, just like Einstein's equation, even with relativity is still being validated through experiments today, that later on, through even better experimental techniques, they validated these two statistical theories. So this is called the log law of the wall. And here are, of course, the coordinates on the x-axis, which are out for your fourth computer project. I'll rewrite these again down for you, but you can go back here. So this is nothing but the velocity, the outer velocity, that's u infinity, at the edge of the boundary layer divided by the friction velocity. Y plus is the friction velocity times the distance from the wall divided by viscosity. So you see that's really a linear function because at any position in the boundary layer, Utah and viscosity are not changing. So you can almost say this is a linear distance, but it's plotted in the log domain, and U plus is also log. One other thing that changes, which is a little bit troubling, is with higher Reynolds number, this value, of course, of U plus can go higher. So when I was a grad student, I didn't understand that, and I kept trying to force my profiles to go to a value of 25, because in the book I had the example composite profile. The composite profile is this whole domain went up to 25. So I spent a lot of time and wasted time trying to force my profile to do something it wouldn't, because I knew if I did it correctly, I would have this condition, U plus Y plus equals 1, and the outer part of there going to say like a value of 25, but that's not a requirement. So anyway, we've developed really only this log part of the profile. And people worked really hard to try and create composite profiles, just one equation that represents this whole thing, which would be the black line. And that's also kind of interesting. So let me get my notes over here. And I've already said a lot of the notes verbally about this graph, but just to fill it in, the most important points, there's 3 distinct regions. And on figure 1.12, which I already pointed out, remember U plus equals Y plus equals 1 at Y plus equals 1 from wall. And of course, the majority of boundary layer is dominated by the log layer. Just like most of the cascade of Kolmogorov, that spectrum is dominated by the inertial subrange. In the interest of time, I'd like to focus on the most important things. I would like to note how that outer layer was developed. And I'm going to talk about that verbally. You have most of the notes already, which are filled in. And I would like to go down here. And you can see figure 1.13. So in this figure, we have Ks, and Ks is a roughness variable. So this is increasing roughness. And C is the plus C term in the profile. Okay, and once again, there's many decades of roughness, but generally low roughness is in this region here, and you'll see C is equal to 5 for smooth walls. Okay, so if you have very rough walls, meaning that all of a sudden the roughness gets to be on the order of a few mean free paths or more. Then the fluid kind of gets trapped in the roughness on the wall, and this is purely an empirical calibration of that coefficient. So if you come back here and look at the log law of the wall, that's just that linear term. So you can imagine in this equation here, if C is decreasing, you can see this profile essentially will be going down and at the outer part of the layer to match it. So that's found empirically. It is an empirical coefficient which is calibrated. But you see for a whole decade, if you have a smooth wall, even like a sandpaper, C will still be about 5 for these flows in practice. Then you're going to see more empirical forms, and this is what we call a composite profile with Cole's wake strength parameter. So this is a modification of the typical log law. So let's look at this one, and you'll see this a lot. This equation, or part of the equation right here, this is the traditional log law equation. Okay, and C is this parameter here. K is 0.41, Y plus is non-dimensional distance from the wall, or we call that the inner coordinates, and U plus is non-dimensional velocity normalized by friction velocity. So it happened to be that Cole in 1981 proposed this term. And so you might look at this term like sine squared. So how, sine squared increases, unlike cosine, right, near 0, when you're increasing in the argument. And so he squared it to keep it positive. And here's kappa, and then there's y. Delta is the boundary layer thickness. So this is a purely empirical form here that matches the data really well. Pi is just a factor. It's not a Buckingham pi factor, it's just a factor. And this is added on to the log law of the wall to complete the composite profile. So if you go back here, if you plotted that equation, I'll write it in orange, you'll get this. You get a line that looks like this. And so if you're comparing your predictions, like for typical flows, from say CFD or turbulence model, you can actually plot on, say, this form, which they call composite profiles. And it's probably the first one that's most used. Now pi actually has a special meaning. It has to do with pressure gradient. So here's Cole's wake strength parameter. Pi is a functional pressure gradient. And there's the original paper if you want to read it, Coles and Hurst, 1969. So this is non-dimensional pressure gradient. Right there. And then there's pi, which is in the numerator of this equation. So here's 0 pressure gradient flows, and it takes in a value just above 0. Because of course it was 0, it wouldn't be very meaningful. If you increase the pressure gradient, it becomes higher, and that would have the effect of raising the outer defect layer. And if you have a negative pressure gradient, then the layer would go down, which makes sense. If I have a favorable pressure gradient, negative partial P partial X, it makes a lot of physical sense for my boundary layer to be thinner, right? So delta would go down. That's exactly what you're seeing in this region, right in here. Your pi factor is going down. In fact, so much so if you have very, very favorable pressure gradients in your flow, you would imagine that the outer defect layer would become even smaller. Adverse pressure gradients, which is of course partial P, partial X, that's derivative pressure in the X direction or flow direction is greater than 0. That's a adverse pressure gradient, right? So static pressure is increasing as you go in the flow direction, then the defect layer would increase. Okay, and I've defined your pressure gradient formula right here. Okay. One last note. It turns out, of course, they tried to developed this pressure gradient formula, so beta T is, doesn't vary much, but it is non-constant, of course. And if it doesn't vary too rapidly, then this is a good composite formula. For boundary layers. But you see it is an empirical fit model based on the sine squared function. And it just turns out that's an excellent empirical model to match tons of measurement data through adverse and favorable pressure gradients with raw wall roughness. And there is, just as another note here before we take a break for maybe 10 minutes, is that in Pope's book on turbulence, which is one of my favorites, and he was a professor at Cornell and Aerospace, he gives lots of examples of even better composite profiles for wider variations of flow. And that's like a book that was often used to teach students in turbulent combustion. So I think it's an amazing book, and I would like to just, if you're curious about more of how this is explained, that's where I would direct you. So what we're going to do now is we're going to take a 10-minute break and come back in, 12:55. And then I want to look at the paper of Lorentz, which I passed out on Thursday. And we'll talk about the paper and then pass out the computer project and talk about how to program it. So thank you.